Welcome to week four, Introduction to Machine Learning. Uh, I'll share my screen quickly. All right. So everybody can see my screen, right? Both in YouTube as well as in Gmeet. Okay. Okay. Yeah. So yeah. So do you have any particular questions from previous or anything from? Do you have like? Can you like get the week four lecture, like whatever has been taught in week four? Did you guys understood everything, or is it any part which you couldn't understand, or you find need more clarification? Okay, maybe as we start our session, uh, maybe we can get more questions, and we can address those questions uh, as we go on, right? So yeah. So this is Introduction to Machine Learning Week 4. My name is Rohan Raha. I'm a PMRFTA for this course. I'm a PhD scholar in the uh, ISC Bangalore, Indian Institute of Science, Bangalore. So yeah, all the previous weeks recordings, recorded lectures, notes, PPTs, and uh, notebooks like Python codes. Those can be found in my YouTube channel. So YouTube contains all the recorded lectures, and in the description of the lectures, or in the comments of the lectures, I posted the link for where you can find the uh, the notes and everything. Right. So week three. Okay, someone is saying week three is not available on YouTube. Week three is actually available. So okay, I can quickly share you the link for. I mean, you can go to my channel again, and uh, you can find the week three lecture. Okay. Week three is available actually. Okay. Okay. You found it. Okay. So yeah. So let's start with this week. So I mean, week four lectures contains naive Bayes algorithm, Bayesian networks, and those things, but they were like knowledge of probability and statistics, some basic knowledge, right? So in this lecture, I will focus on the mathematics. I will move on to the actual machine learning algorithms, machine learning platforms, right? I think some of the parts in probability and statistics were not, explained in detail in the videos for the week 4, and delve into the basics, fundamentals of probability and statistics, and then I will go into it. So someone has raised a hand. Question. Goras has raised a hand. Okay. Okay. So before I go into the slide, uh, this lecture I think I should. But before that, I want to make sure that we are clear on some of the definitions of probability. So yeah. So we'll start with the very basics, and then we'll do the ML part. So okay. Let's see. Okay. So so I guess all of you are familiar with you know uh, probability at high school level, or something like that. Basic, you know, what is the basic definitions of probability and all. Like if not, and like we'll do it again. But uh, yeah, if you are, then it might help you. So okay, with that, let's start. So there are like a few definitions that I want to make it clear before we go into numericals. So first is experiment. So what is an experiment? So experiment is something when you uh, perform a task which has some outcome. Uh, I mean, it's very hard to objectively define an experiment, but with I can give you some examples which will help you understand better. For example, you're tossing a coin. You're doing some task, tossing a coin. The coin lands on heads or tails. So that is the outcome of your experiment, and the task is you're tossing the coin. So that is basically an experiment. The whole process, right? Next term that we'll see is sample, right? So experiment, as I said, is tossing a coin, or rolling a dice, for example. That is a good experiment as well, right? Now, sample. What is the sample for the first experiment? Let's consider the first experiment. What is the sample for tossing a coin? Like you can get either heads or you can get tails. So that is your total sample space, right? You cannot get anything other than that. Right? What is the sample for rolling a dice? You can get a value of 1, 2, 3, 4, 5, or 6. A six-sided dice, right? This is your whole sample space. Okay. Now, event. Okay. So event is, you know, you are, selecting a particular value from your sample space. So let's say, your x is some variable which can take either heads or tails. So x is the outcome of your experiment, which is tossing a coin, right? And that variable can take either heads or tails. And the event is when x takes a value h. That is one event. Or another event could be x takes a value tails. Okay, right? So that is another event. So these are events, right? So from the very basics, as I said, I will explain everything from the very basics, from the definition and all. So is it clear till now, or you need any clarifications? We're just getting started. Okay. Okay. Right. So, okay. Now, before going into the definitions of probability, let's look at one rule called multiplication rule. Okay. So, I'll explain it with an example first, and then I will describe the rule. So let's say you go to a shop, you know. So you can either buy ice cream, or you want to, drink, some soft drinks. Okay. So you have two choices, right? Now, if you decide on choice ice cream, you can choose whether you want vanilla flavor, whether you want, butterscotch, or maybe you want, let's say, chocolate. Right? On Coca-Cola, Pepsi, or let's say thumbs up, right? So yeah, now so this is more like a diagram, right? So what it says that you go to a shop, you have initially you have two choices. Okay, so this is the result of your first experiment. Okay, let's consider this to be a first experiment. So what is this experiment? This experiment is basically uh, you want to choose between ice cream and soft drink. This is your first experiment. Second experiment is that if you, let's say, choose between ice cream, choose ice cream, then you get to choose you know three more flavors of ice cream, and if you choose soft drink, you get to choose between three more flavors of soft drinks. Okay, so this is your second experiment. So you're doing two experiments, right, simultaneously. And the outcome of the first experiment is either ice cream or soft drink. Outcome of the second experiment could be, these things for ice cream, these things for, soft drinks, and so on, right? So the multiplication rule says that if you have, you know, n1 outcome for n1 outcomes for first experiment, and corresponding to each of those n1 outcomes, you have n2 outcomes for so on. You will end up with total n1 times n2 times dot 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 times of outcomes, total outcomes, right? So that is basically okay. Let me see. It's getting out of the screen. Okay. 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 So basically, yeah, this is the multiplication rule for n1 outcomes. For each of those n1 outcomes, if you have n2 outcomes for the second experiment, your total outcomes will be n1 times n2 times dot dot dot. So basically, for the first experiment, you have two outcomes here. For the second experiment, for each of those two, you have three more outcomes. So total number of outcomes will be six. These are the six outcomes. So it seems very simple and trivial, but how these simple things will lead to very will be very important while calculating probabilities and so on, right? Okay. Another thing I want to highlight before we go on to describe probability. So let's see. Okay, I'll write it here. Okay. So this is basically part of something called combinatorics. Okay, uh, you might have heard it in high school or so on, but we'll need only one result from this. So let's say you have n items, could be anything, n balls, let's say, or n boxes or whatever, n identical items, and you want to choose k items from there, you know, without replacement. Okay. Okay. So you want to choose k items from the n items without replacement, right? So first part is order uh, matters. Okay, let's consider this first. So by order matters, I mean, like, if you choose the okay. So I think I misspoke earlier when I said identical items. Let's consider distinct items for now. Okay, these are not identical items. These are distinct items. Let's say if you have like 10 balls, they will be numbered like 1, 2, 3, 4, 5, 6, 7, 8, and so on. So okay, so you want to choose uh, k balls out of n balls, and the order in which you choose the balls, that matters. So if you, let's say, picked up the uh, number 5 ball first, and number 2 ball second, and the other way around, if you picked up the number 2 ball first and number 5 ball second, those two are distinct ways, right? Different ways. So basically we have to calculate in how many ways can we like do this. Can we pick k items from n items um, without replacing them, and the order will matter. So there is, like, for the first item, you have like n number of choices. You can pick any one of the n items, right? You have n choices. For the second item, you have n minus 1 choices. So this is again like coming from the multiplication rule, right? For each of the n balls you have picked, for picking the second ball, that is performing the second experiment, you have n minus 1 choices. So we'll multiply this, right? N minus 1. And then again, for taking the third ball, you have n minus 2 choices, right? And so on, right? Till n minus k plus 1. Okay, right? Is that fine? We're just using the multiplication rule that we just used earlier. Is it fine? Uh, okay, okay. Let me. Is it fine now? Okay, now it's better. Okay, okay. Now the second part is where order doesn't matter. So again, like, you just need to find a group. So for example, this will be helpful when like, you are, let's say, you're forming a team. You want a team of uh, let's say 3 people, and you have 10 persons in choice, right? So let's say, the uh, let's say, BCCI is forming the cricket team. They want like 15 players from a pool of, let's say, 100 players, right? So your n is 100, and you want 15 players. Your k is 15, right? So you just want to, I mean, order doesn't matter, right? You pick Virat Kohli first and Rohit Sharma second, or Rohit Sharma first, Virat Kohli second, doesn't matter. They will be in the team together, right? So this is the place where, this order doesn't matter part comes in handy. And so the question is, like, in how many ways can you uh, can anybody tell me the answer? Yeah, cricket team or football team or so. What is the answer? Can anybody tell me? Or like you don't know? Should I go into details? Yeah, Pritham is saying NCK. Everybody understands like what is uh, NCK, right? Or N choose K and so on. Okay, right? Okay. So the answer is like, yeah, 100 choose 15 or 100 CK, whichever way, like 100 factorial divided by, you know, 15 factorial divided by 100 minus 15 factorial. Okay. In general, n choose k is equals to n factorial divided by k factorial times n minus k factorial, right? So this will give you the value of number of ways you can choose uh, 15 people out of 100 people, right? Okay, so uh, okay, so in the first part, right? Okay, that's actually a very good question. Why it is n minus and why not n minus k? Uh, n minus k, yeah. So basically, if you see, you want to pick k items, right? So let me explain it this way. Like if you had to pick, two items, let's say k is two. Okay. So what will happen is what will you do? You will choose n for the first item, and you have n minus one uh, possibilities for the second item, right? Plus one. If k is two, this will give you n minus one, right? So if you go till n minus k, then you will, have an two. So we'll have three terms, right? Is that clear? Okay. Yeah, but that's a very important question uh, because that is pretty confusing sometimes, right? So you have to keep in mind that, so basically in this series, this is actually the kth term, not the k plus one term. This is the k minus one term, not the k minus one term. This is basically the kth term. So you are choosing, if you count, one, two, three, four, so on, this will come out to be the kth term. So you need to choose k items and you need to stop at the kth, right? So I think that is clear. Okay. Uh, okay. Uh, which is not clear, and you don't understand NCK or okay. So the concept is again, as I was saying, with the example that you need to pick a team of 15 out of a pool of 100 uh, people. So it doesn't matter if you pick let's say Virat Kohli first or you pick Rohit Sharma first. It doesn't matter. They will be in the same team, playing in the same team. So in the first part, you are like ordering the people. So if you are picking a team and you are ordering them in terms of their playing position, then this is the number of ways. The first part is the number of ways. If you want to pick a team and arrange them in the playing order. Whereas in the second, what is asked is you don't need to arrange them in the position play, but you just need to select the group which will be playing. Clear now? Okay, Mr. Mova has raised a hand. Yeah, Mr. Mova. Okay. If not, let's move on to the next topic. Okay. Okay, let me open a new uh, tab. Okay, let's see. All right. Now let's let's go into the definition of probability. Okay. So I will define probability in two ways. Okay, one would be the very naive definition, another would be a more formal definition. So naive definition is so you have let's say again let's go back to a favorite example like tossing a coin, but this time instead of tossing one coin, let's make it a little challenging. Let's toss the same coin but twice. Okay, or you can see it as tossing 2 coins, or yeah, similar. So what will be your sample space in this case? So your sample space could be, you get head in both the coins, or head in the first coin, tail in the second coin, and the reverse thing, tail in the first, head in the second, or tail in both the coins. Okay. Now someone asks you that what is the probability that you get head in both the coins, right? So the naive definition is actually number of favorable outcomes divided by total number of outcomes. Okay. So in this case, what is your favorable outcome? Your favorable outcome is only, heads, this thing, both heads. So that is one. Divided by total number of outcomes is basically four. These are all the four outcomes that you have, right? So that is the, very naive definition of probability, right? Is that fine? I think this should be okay. You can come up with other examples of your own. Okay. Now, going into the more formal definition of probability, which is a more like an axiomatic definition of probability. So here, let me first draw a picture. So let's say this is your sample space, okay, and you have various points in your sample space. Each of the points represent each of the outcomes. So let's say this represents, HH, this represents another point represents HT, another point represents TT, and so on. Like you could, you know, toss 1,000 coins and your sample space will be filled with, many more outcomes and, you know, and this is basically your sample space. This is basically all the points in your sample, the points, all the outcomes basically, right? Now think of probability as a function that maps all the subsets of all the possible subsets in your sample space to a number between 0 and 1, both inclusive, right? uh, is that making sense? Am I being too abstract? Sorry, which is not okay. So you know what a function is, right? A function is something which maps anything from domain to a range. So function. So let's say this. This is HH. This point in the sample space represents HH, as we were seeing in the previous example, right? And probability is basically a function or a mapping which takes HH to the value 1 by 4, right? So as we saw in our earlier example. So therefore, if you put machine, you give it some input, it gives you an output, right? That's the simplest way to look at it. You give an input HH to it, it gives you an output 1 by 4. If you give it an input, let's say HT, it gives you an output again 1 by 4, right? Or, in this case, 1 by 4 could be any other number in general, okay? It's just a machine which takes an input from your sample space and provides you an output of number between 0 and 1. Is that clear now? Okay. Okay. Uh, uh, but I think if there is some particular question, we might answer that, but the Bayes theorem and all those things. But yeah, if so we'll cover a little bit about distributions, little bit, but yeah, we'll not go into much detail. First rule is that the probability of an empty set is equals to 0. Probability of the total sample space is equals to 1. That is the first rule, right? Now, so again, what is empty set? So this is your sample space. So what is that, this whole sample space occurs? It is 1, right? Even if like, any particular event from the sample space occurs, uh, that is included within the sample space. The sample space is represented by S. So probability of S is 1. So all all the outcomes are within the sample space. So the probability that an event occurs within the sample space is obviously 1, right? It has to occur. Whereas null set is the outside of the sample space, whichever is not contained in the sample space. So that probability is 0 because all your outcomes are contained in the sample space. So what is the probability that some outcome outside the sample space occurs? It's 0, right? It seems pretty trivial, right? But this will have very big implications when we derive some of the rules. Okay, second axiom is if you have let's say a1, a2 dot an, these are n disjoint uh, samples, or n disjoint events, or sub. Yeah, I will write events, let's say. Okay, yeah, I'll write events. So if you have n disjoint events, probability of the summation of union of all the events E2 occurs dot probability of the individual events, right? AI. So then plus P of A2 plus till P of AN. Right? I'll explain this axiom one with the help of something called Venn diagram, right? Let me just explain it first. Okay. So let's say this is your sample space, right? And this is, instead of considering n events, let's consider two events. So this is one event A, this is another event, let's say B. And this part is basically where both A and B occurs. A intersection B. Right. So okay, first let me do one thing. Instead of considering, because in the definition, as I mentioned, you have two disjoint events, right? A and B, right? So this is the meaning of disjoint. So disjoint basically means, if A occurs, B cannot occur. In other words, they are like mutually exclusive events. right? So if you see, this is the event A and this is the representation of event B. And if A occurs, B basically cannot occur because they are separated, they are mutually exclusive, right? So what the axiom tells is that P of A union B is basically plus P of P. So if you want to see, uh, so let me think of an example, right? So previous example, like tossing two coins, right? So you're tossing one coin and you are getting head. So probability of getting head from the first coin is half, right? H1. So you know so in the earlier case, while we are looking at this example, these two, when you are looking at the sample space, these two are not disjoint events, right? So one event are not mutually exclusive, so we'll have some intersection, right? But imagine, if you have events which are mutually exclusive, so in that case the probability will basically add up. So let's say if you have like probability of event A and probability of event B is this thing. Basically, what will happen is P of A union B is basically 1 by 4 plus 1 half. That will basically be, 3 by 4. That's it. Right? So is this clear? The only condition is that you can sum up probabilities when the two events are disjoint or mutually exclusive. Right? Okay. If the two events are not mutually exclusive, let's consider this diagram. Okay. This left side. So you have two events which has some, intersection, some P of A intersection B, right? Uh, Let me give one example. Let me think of some example. I think that will make it more clear. So let's say, you have, so in a class you have number of students is 100. Out of that, number of males 60, number of female, let's say 40. Okay. And number of uh, students uh, who has let's say who has passed the exam is 70. Number of male students passed is, let's say 30. Number of female students passed is 40. Right, this is just a random example. So okay, so A represents the number of students who has passed. uh, Wait a minute. Okay, so let's consider, uh, let me think of another. Let's forget this. Let me think of something which makes sense. Okay. Okay, forget about it. So let's say A represents the number of students who has passed in maths. Okay, let's forget the male-female comparison, male-female example. So number of students who has passed in maths. Okay. So that is, let's say 70. Number of students who has passed in science. A represents the probability that uh, a student has passed in maths. probability that, and B represents the probability that a student has passed. So P of A intersection B represents the probability that the students has passed in both the subjects, science and maths. Example. Okay, is that clear? Okay, so Kavita is asking when said multiplication rule is uh, so do you mean multiplication addition in case of probabilities like P of A union B and those things? So if you are talking about that, then I will explain in a minute when to use multiplication. So right now we are just adding up. We are just using addition because come to the multiplication part. So right now we are just adding up PA plus PB and calculating the total probability, considering that A and B are disjoint. But here, as I said, the events are not disjoint. So how will you calculate P of A union B, right? So that is the question. So if you see my screen, okay. So how will you calculate P of A union B? So you can break this. So this is the shaded region is A intersection B. To calculate what is the probability of P of A union B, this whole red shaded region. So the black shaded region is basically P of A intersection B, and the red shaded region is P of A union B. Okay, that I want to calculate. Yeah, that includes like you can basically that means in the previous example that I was giving, that means you have passed in either maths or physics, like not either, like if any one of maths or physics or science, whatever. So if you have passed in maths or if you have passed in both or any one of them, at least one of them. If you have passed in at least one of them, what is the probability? That is basically the example. Is that clear now? Whereas pay intersection B, that means you have to pass both P in both math and science. You understand the difference, right? P of A intersection B and union B. The probability, as I said. So considering, the second axiom, we will consider the second axiom. So as I said, A and B are not disjoint here. So what we will do is we'll break this whole set into two disjoint. So complement represents whichever is not in the set A. So if you see, P of A is this thing, this yellow shaded region, this is the whole P of A. Whereas if you see, P of uh, let's say P of B intersection A complement. So B intersection A complement is which is common between B as well as A complement. This is the green shaded region, which I am showing here, right? This is the green shaded region. So this term basically means the second term basically means that it should also contain in B as well as A complement, right? Now what we will do is we will break the second term into uh, two other terms, which is P of A minus P of A intersection B. Sorry, P of B minus P of A intersection B. So you can write the green shaded region as P of B minus the P of A intersection B, right? So the green shaded region is P of B minus the black uh, black line shaded region, right? Is that clear? So that's why the formula comes out to be like this. Yeah, this is basically the formula, right? P of A union B is P of A plus P of B minus P of A intersection B. Is that right? Or do you have any question? Okay. So from the first line, I am just writing PA as PA. Now I am writing this term, the second term, as this thing. That's just it. The second term basically represents the green shaded region, right? And the green shaded region can also be written as P of B minus P of A intersection B. That is the If you like, P of B is again this whole circle minus, if you just subtract the P intersection B part from, no, green part. So the green shaded part is basically P of B intersection A complement. Uh, P A intersection B is not the yellow part. That is the black part in between, which is common between both A and B. That is the this part, black shaded part, right? Yeah, which is basically the green part, right? That comes, so, right? Okay, okay. So I'll just go back to my slide once and just, basically the first thing that I was trying to say, the formula P of A union B is equal to that thing. Again, if you see, this is the part B, P of B intersection A complement, and then you get the addition rule, right? This is the addition rule. So the first one is for mutually exclusive events. The second one is for, you know, non-mutually exclusive events, right? And now here is another thing which is called the law of total probability. Again, this is a very, very useful thing, and it simplifies a lot of problems. And okay, so I haven't gone through, conditional probability. I'll come back to this after I, talk about conditional probability. Okay, I'll come back to this law of total probability. Okay, so what is conditional probability? So, so you have understood, P of A, P of B, P of A intersection B, and so on, right? Now, if you are given something and you want to calculate the probability, right? If you know some information prior, beforehand, and you want to calculate the probability of something by knowing that information, so basically you're conditioning on, you have some condition, that, okay, I know this, and then what will be a probability of something, right? So for example, if I, go back to my tossing of coin example, right? If I go back to the, yeah, tossing, right? So if I know that uh, the first coin is basically giving me, if I know that out of the two coins, the first coin is heads for me, okay? Then what will be the probability that, the second to find? So in this example, let's consider, I want to calculate the probability that the second coin gives heads, given that my first coin is head, right? To calculate. So if you see from this sample space, which are the examples, which are the events that shows that, first coin is head. So this is the first coin is head, and again this one. These two are the only uh, events uh, which shows that first coin is heads. Now we want to calculate what are the chances that my second coin will also show heads. So that will basically, so your sample space is now reduced to only these two values. Your sample space is now only, this is the sample space, right? Now between these two, you want to calculate what is the probability also shows heads. So that is basically only this is your favorable outcome. So 1 by 2. Out of 2, you have only one favorable outcome. So you see your probability has now increased. Your probability has been refined. Your probability has changed because you are adding one condition to it, right? So previously, the probability of head was 1 by 4. Now, since you know that the first coin is head and you want to calculate what is the probability of the second coin, this probability has increased, right? So this is a very, very powerful tool. And yeah, so we'll see how it is used in future. Okay. So, okay. Yeah, for by P of P, right? So again, I will explain through this example again. So P of H2 given H1 is basically P of H1 intersection H2 divided by uh, H1, right? So you have to calculate what is the probability that both are heads. So H1 intersection H2 is that. What is the probability? That is 1 by 4. If you look at the original sample space. So now we will go to the original sample space. Okay. So what is the original sample space? HH, HT, TH, TT. Okay. So now what is the probability that both are heads? That is 1 by 4. You know. So in these two are the favorable outcomes, right? 2 out of 2 by 4. So this will basically give you half. Again, you see that is the same thing that we are getting. So explain the intuition, like why the formula is this, and this part shows that the formula actually works. The second part shows that okay, the formula now works, right? So is there any question now on this conditional probability? All right. So yeah, one comment on this is that so if P of H2 given H1 is uh, basically H2 if H1 and H2 are independent. So this is the condition for independence, right? So what does it mean? That you're tossing two coins. So the result of one coin is not dependent on the result of the second coin, right? Because you're tossing different coins individually, considering that both coins are fair and the tossing of one of the probability that you get heads on the second coin is simply P of H2. And what is the probability that you get head on the second coin? Yeah, right? So again, all these things, this example can, is explaining all the things that I have, like the example has explained what are, as well as, conditional probability and, uh, you know, of events and so on, right? So, yeah, any questions? And again, if two events are independent, then P of H1 intersection H2 should be equal to P of H1, right? So again, so someone was asking like where to use multiplication, Kavita. So the dependent events, if you want to calculate what is the probability that both the event occurs, then you have to say that okay, P of what is the probability that I get head on the first coin? That is half. What is the probability that I get head on the second coin? That is also half. You get 1 by 4, right? Somehow in the notepad. Mm, Okay, I think I should move on to the slide. All right. So I think yeah, that is it. Okay, so someone is asking P H1 equals P H1 given H2 is H1. Uh, yeah, so for for two events to be independent, you need to have basically equals to P of A and P of B given A equals to P of B. You need to two events are independent. Okay. Yeah. So basically, P of H1 given H2 should also be equals to P of H1. Okay. So this step, yeah. So I'm saying, yeah. What I'm this condition has to be satisfied for H1 and H2 to be independent, right? Any more questions? Okay. Then, if not, yeah. Now, the total probability, law of total probability, and then I will explain what is Bayes theorem, right? Okay. Let me see. So, like, am I going like too abstract with the definitions and all, like, or is it understandable? Or all these things, should I like speed it up? You know, what do you think? Is it too trivial or abstract, or is it okay? It's okay, right? Okay. Okay. Yeah, because those are required for, uh, to basically understand the Bayes theorem. I think if the lecture contains too much mathematics as well, and you require this mathematics to understand the lecture. So that's why I'm doing these things. And you will have a lot of questions in the assignment as well based on probabilities and basics of Bayes theorem and those things. So this will help you solve the numericals as well. So again, so yeah, two things that I will explain more. That is, you know, law of total probability and then Bayes theorem. Okay. So let's start with law of total probability. Okay. So, I think some of you might have heard about Richard Feynman, who was a great physicist and solving a problem, right? So, um, basically, uh, I mean, Richard Feynman, apart from being a great scientist, he was a excellent teacher. I mean, very good teacher, right? He was famous for his more for his teaching than for his research, maybe I don't know. So he said that in order to solve any problem, you look at the problem, understand the problem, and then you think very deeply about it, and then you solve the problem, right? So that was what his answer was. That pretty much made no sense, and I don't know how that will help people to uh, you know solve difficult problems. But here we will look at one example where we can solve very difficult problems. This is basically a very strong, powerful method to you know solve difficult problems. And uh, so okay. So let's say you have this sample space, and you want to find the probability of an event X in this sample space. Right? So P of X is what you need to find. So what you do is basically, um, as I said, that you have to divide your problem into multiple parts, multiple disjoint parts, and then attack the problem one part at a time. So let's say you divide your sample space into four disjoint parts. Let's name the parts as S1, S2, S3, and S4. So now you want to find the probability of X after you have divided the sample space into four disjoint parts, right? So what you do is, you find probability of X given S1. So you consider the S1 part only first, and you find the probability of X given that you are in this S1 part of the whole sample space, right? And then you multiply that by the probability of choosing this part of the sample space, probability of choosing S1, right? And similarly, you do it for uh, given S2, probability of S2, and probability of X given S3, given like, and the probability of choosing S3, and similarly, probability of X given S4, and multiplying it with probability of S4, right? So, yeah, so you have to divide your whole sample space into disjoint parts, which simplify your problem, and then consider each part at a time. Find the probability of X given that you are in that part, and multiply it with probability of choosing that part, and do the addition. Right? That's basically the law of total probability. Right? So I think it will be even more clear if I give you an example. Right? So let's say you know your example is, let's say you're given one bag. You're basically given two bags. Okay, bag one, bag two. So bag one has seven red balls and three green balls, whereas bag two has two red balls and eight green balls. Right. So let's consider the balls to be identical, and you have, you know, yeah. So there are two bags. Now, what you have to find. So you perform this experiment that you choose a bag at random out of the two, and then you draw one ball from that bag, right? So uh, now you have to find what is the probability that the ball you have drawn is a green ball, right? So this is what you have to find. Probability of that ball drawn is green. So uh, yeah, so what you do is you basically uh, divide your problem into two parts. So let's say that the probability of green ball given that you choose bag one times the probability of choosing bag one plus probability of green ball given that you choose bag two times the probability of bag two, right? So this is how you divide your problem into two disjoint parts. In one case, you are choosing bag one. In the other case, you're choosing bag two. And then you find the probability of picking the green ball, provided you choose that that particular bag. Right? So what will be the probability of a green ball given that you choose bag one? So that will be basically 3 by 10, right? Because you have three green balls in bag one, and you have total balls are 10 in the bag one, right? And similarly, what will be the probability that you choose green ball given that you are in bag two? So that will be 8 by 10, right? Because you have eight green balls, and total you have 10 balls, right? Okay. And what will the probability of B1 and B2? So given that you're choosing the bag at random, so the probability will basically be half, right? So basically that means that you don't have any particular preference of choosing one bag over the other. So there is it has equal probability. You have equal probability of choosing bag one or bag two. Right? Okay. So yeah. Is there a question? Okay, so Monica is asking why is the probability of bag one is equal to half? Okay, so yeah, this will be basically be given in your question. So P of B1 is basically the probability that you choose bag one. And so considering that, both the bags have equal probability of being chosen, you don't have any preference of choosing one bag over the other. I'm considering that, both bags have 50-50 chance of being chosen, right? And so I'm assuming that, one bag is not more beautiful than the other. In that case, you would have, you know, uh, choosing one bag. Would have more preference of choosing one bag over the other, right? So yeah, so I'm considering that, both the bags have equal probability of being chosen, and in that case, it is half 50-50, right? Okay, so if you calculate this, you will get the probability of a green ball. Uh, yeah. Okay. So now we will move on to the next topic, that is Bayes theorem. Okay. So okay. So we have previously we have studied conditional probability, and from the formula for conditional probability, I will derive the formula for Bayes theorem. Okay. So uh, so let me just write out probability of A given B. So that is P of A intersection B divided by P of B, right? Okay. So from here we can get P of A intersection B equals to P of A given B times P of B. Similarly, we can have P of B given A as P of A intersection B divided by P of A, right? And from here again, we'll get P of A intersection B as P of B given A times P of A, right? Okay. Now, how to derive the formula for Bayes theorem is you just equate these two, equation 1 and 2, right? So from here, you just equate P of A intersection B to each other. So you will get P of A given B times P of B equals to P of B given A times P of A. Okay. And from here, you will get P of A given B as P of B given A times P of A divided by P of A. Right. So this is basically the formula for Bayes theorem. Okay. Right. So this is Bayes theorem. All right. Okay. So moving back to my slides. Okay. So if you see here again, you can see that P of A given B is P of B given A times P of A divided by P of B. Right. So what is the usefulness of this theorem? Why do we need this theorem? So we will see that in practice when we do naive-Bayes algorithm. So sometimes you would know the P of B given A, right? And you will know this probabilities P of A and P of B. And you have to calculate P of A given B, right? So in those cases, it will be very useful. And so basically, P of B given A is called the likelihood, and P of A is the prior probability. This is the probability that you know prior before doing the experiment. So this is the probability that you know beforehand, priorly. Okay, and P of B is marginalization, whereas P of A given B is called the posterior. So these are just the terminologies that are used. Okay, all right. So so let's go back to our coin toss experiment, right? So basically, what we are doing is we are just tossing a coin, and we are saying that okay, if it can land on heads or it can land on tails, right? So what we are doing is that we are representing you know this heads as, let's say, 1, or tails as 0, right? So okay, this is not the probability of heads. This is just representing heads as 1 and tails as 0. So I'm trying to generalize this idea that you're doing an experiment and you have basically two outcomes, right? So it could be anything, right? So coin toss is yeah, tossing a coin is just uh, one example of it, but it could be anything. You're like playing a game, and the output could be you win the game or you lose the game, right? So, and so on. What I'm trying to say is that in any experiment where your outcome is binary, you can represent it as 1 or 0. So I'm taking the example of coin toss. So I'm saying that, okay, I can represent heads as 1 and tails as 0. So let's say, you represent the outcome with the random variable x, and you are saying that probability that x equals to 1. In other way, you can say that probability that the coin lands on heads, that equals to p. Okay. So this is not 50-50. Like, the probability is not half, because it might not be a unbiased coin, right? The coin is biased. So p could be any value between 0 and 1, both inclusive, right? So it's a biased coin. So such that the probability of it landing on heads is uh, could be more or less than probability of landing on tails. Okay? And the probability of landing on tails, that is probability x equals to 0, would be basically 1 minus p, right? So let's say that I represent x as, okay, this is called the Bernoulli distribution. Okay. So what happens is that uh, so what is the probability of x? How do you represent the probability? So it is p uh, to the power of, let's say, xi times 1. I'll explain this in a bit. Okay. Okay. So you see, this experiment has probability that the x will take value 1 with p. Okay, the probability that x will take value 1 is p, and the probability that x will take value 0 is 1 minus p, right? So if uh, x takes value 1, so this expression becomes p to the power of 1, and this 1 minus p to the power 0. So that is basically p, right? And if x takes value 0, then 1, then this will turn out to be 1 minus p. So this is what is representation of this experiment, right? Is that clear? And here we can add one indicator function where we can say that, okay, xi takes values between 0 and 1. Okay, values not in between, but only discrete values 0 and 1, right? So in case x takes value 0, then we'll have probability p, and x takes values 1, we'll get probability 1 minus p. Is that clear? Right? So this is just a Bernoulli trial that I am trying to say. Okay. Now you can repeat this experiment, 100 times, or let's say n times. So then what will be the probability that, of all the variables x1, x2 till xn, let's say. You repeat this experiment n times, then what will be the probability distribution? Considering, again, here the multiplication will again come in. So considering that each of the trials are independent, we will say that, okay, this is equal to P of x1 times P of x2 times dot 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 till P of xn. And each of this will have this distribution. So this will be a product. So this is the product sign of I equals to 1 to n and P of xi times 1 minus P times 1 minus xi. Okay. And with the indicator function, I can indicate that, xi takes value 0 and 1, right? Okay. Okay. Now, let me see. Okay. So we will require this later on, but that's why I just explained it. But let's go back to the slide now. Okay. So in Bayesian learning, so what you are given is that, let's say you are given uh, a hypothesis. Let's say you are given two hypotheses, and you have to select which one is the best hypothesis. So that is the basically the formula for the maximum a posteriori hypothesis. Okay, so I'll explain it with an example. I think you will get it better before with the example first, and then we'll look at the formula, right? So let me again go back to the notepad. I hope it's visible now. Okay. Uh, in the last step in the notepad, you mean? Uh, you mean this one, the product? Yeah, that is just product. I mean, just representing the product of n terms. So it will just represent, n times this thing. This will be basically this n times. So each of the p of xi's, each of this term is basically this term, right? Uh, and x2 will similarly be again this term, and so on. Like this is just the product representation. Is that okay? All right. Okay. So okay, let me explain maximum a posteriori hypothesis. Okay. So let's say you are playing a game with your friend. Okay. And um, you're just playing a game. Let's say you're tossing a coin, and if it lands heads, you win. If it lands tails, your friend wins, or maybe vice versa. Okay. Whatever. So you know that your friend is uh, you know from before that, okay, your friend is he's a very dishonest person. Okay, so he has two coins. One is a fair coin, another one is a unfair coin, right? So the unfair coin will be biased and it might give more probability of heads, whereas the fair coin will be non-biased and it will have 50-50 probability of heads and tails. Okay, so let's say uh, you know uh, the probability that your friend brings a fair coin is low. Let's say it's zero point 0.2. Whereas the probability that your friend brings a unfair coin is high. Let's say zero point 0.8. Right? Now you have to find out your problem statement is that you have to find out whether your friend has actually brought a fair coin or an unfair coin. That's what you have to find out. Right? So uh, what you do is okay, and one more thing was given is that probability that for the unfair coin probability of that the unfair coin gives heads is more, let's say 0.7, whereas the probability that the unfair coin gives tails is 0.3. Okay, this also you know. Now you have to find the maximum a posteriori hypothesis P of y given x. Okay. So now what you do is your friend has brought a coin and you do an experiment with it. So what you do is you toss the coin twice, two times, and both the times you got heads. Okay. So what you do is P of x give x equals to 2h. Okay. Both the times you got heads. You got two heads. Uh, okay. Now, what is the probability? Okay. So, what is the probability that you get heads two times given that your coin is fair, right? We have done this, right? So, this is the first head is has probability half, second head has probability half. So, considering that both the events are independent, we'll get probability of 1 by 4, right? Similarly, what will be the probability that you get two heads considering that the coin is unfair? So for first head, the probability is 0.7 times, again, second head 0.7, that is 0.49, right? So this is the probability that the coin is, you get two heads given that the coin is unfair. Okay. Now, okay, so this is what has been given, right? Now you have to find out, uh, you have to make a hypothesis and find out whether your friend has bought a uh, fair coin or an unfair coin based on the evidence that you get. Based on that, and the evidence is you get two heads with that coin, right? So what happens is that you have to find the maximum a posteriori hypothesis of P of y given x. X is basically your evidence, that is two heads. So you have to find out the maximum possible argument. So y could be fair or unfair. So you have to find out which is giving the more probability, high probability, right? So you have to maximize this probability and you have to see for which y this probability is maximum. That is whether for fair coin or for unfair coin, this probability is maximum. So this is equals to, again, by Bayes theorem, P of x times P of y. There is a normalization factor, but I am just ignoring the normalization factor because that will be basically a constant. So yeah, so basically you have to maximize this P of y given x, right? So let's calculate. So P of y is fair given x, that will be equals to P of x equals to 2h given y is fair times P of y equals to fair. Okay. So what is P of x equals to 2h given y is fair? We have calculated this here 1 by 4. That is 0.25 times P of y is fair. So that you get from here 0.2. So this will give out 0.05, right? Similarly, you calculate P of y equals to unfair given x equals to 2h. So that is P of x equals to 2h given y equals to unfair times P of y equals to unfair, right? So again, reading from the table, we get, you know, 0.49 times 0.8, that is 0.392. Okay. Is that clear? Idea clear? Yeah, that is. So this is the 0.7 where we're getting, sorry. So this is the first 0.7 we are getting. Wait a minute. Okay. So this is the unfair coin. We know that the unfair coin lands on heads 70% of the time, right? And lands on tails. So you have to calculate the probability that you get both heads given that your coin is unfair. So this is given. Now you see what is the probability that I get two heads. So for the first head, you get zero point 0.7, and second head, your probability is again zero point 0.7. As I said, for independent events, you can just multiply, right? So P of x equals to h times x equals to h. 0.7 into 0.7, right? Okay. Okay. So what is the conclusion? What is your maximum a posterior hypothesis? Your map hypothesis case is that the coin is unfair, right? And it makes sense, right? Because your unfair coin gives more heads, whereas your fair coin should give equal heads. So although you have less data points, you have only two heads. You can do it for five heads, or you can do it for any combination, right? So, but whatever the evidence that you are given, that is your coin is landing two heads. Based on that evidence, you can say that there is more probability that the coin is unfair. So your map hypothesis will be okay, the coin is unfair. Okay. Okay. So that is the formula actually. The formula is pretty complicated, but uh, I think with the example, I guess it is more clear. Right? So this is the formula. Again, the same thing. You can go through it, but I guess with the example, it is a bit clear. Now, Bayes optimal classifier. Okay. So, what is a so? mm, Okay. So, okay. Now, Bayes optimal classifier. Now you want to calculate that what is the probability that my uh, y equals to fair given x. So earlier we saw that it is 0.05, right? In the earlier example, whereas probability that y equals to unfair given x equals to 2h, yeah, this is x equals to 2h. We saw it is 0.392. But you see that these two probabilities are not getting added up. And why is it not getting added up? Because we have missed the denominator. We have not taken into care the denominator, saying that the denominator will be constant. But the denominator will help in, normalizing the probability. So that's why the probability of these two are not, summing up to one. So what we'll do is we'll just normalize this, and this is just the simple normalization, and we'll just get 0.11, and in this case 0.89. So the probability that y equals to fair given that you get two heads is 0.11, and the probability that y equals to unfair given you get two heads is 0.89. So this is up to maximum a posteriori hypothesis, but Bayes optimal classifier goes a little bit further from uh, map hypothesis. So what it says that, okay, let's say you've hypothesized this. Okay, you have made a hypothesis that, okay, my hypothesis is that he has brought an unfair coin. But based on your hypothesis, what is the probability that actually it is an unfair coin, or actually it is a fair coin, right? So here you just have a theory in your mind that, okay, he might be unfair with probability 0.89, and he might be fair with the probability 0.11. But what is the actual uh, probability that he has brought a fair coin? So Z represents the variable, that whether it is actually fair or actually unfair, given that Y is fair, right? So this is basically zero point 0.7, right? So you see, given your hypothesis is fair, whether it is actually fair or not, let's say this will be basically given. So let's say Z equals to unfair given y equals to fair. This is something, some value, let's say 0.3. I'm randomly choosing these values, okay? Uh, there is no, this will basically given in the exam. So again, probability that it is actually unfair given that y equals to unfair, that given that your hypothesis is unfair, okay? Probability of z is fair given that y is unfair. This is, let's say, 0.3. This is 0.7. Okay. So I am randomly choosing these values, but you see the meaning of this line should be clear to you. And the meaning is that let's say your hypothesis is unfair. Given that your hypothesis is unfair, what is the probability that actually it is a fair coin? Okay. So your hypothesis is basically wrong, right? Because actually he has brought a fair coin, but you have made a hypothesis that it is unfair. So that probability is 0.3. Okay. This will be given, right? Now what you have to calculate is, okay, actually whether it is a fair coin or not. Z equals to fair. What is the probability that actually it is a fair coin? So how will you do it? You will just see probability of Z equals to fair given Y equals to fair times probability of y equals to fair given x equals to 2h plus probability of z equals to fair given y equals to unfair. Again, you see the law of total probability comes into picture here, given y equals to unfair given x equals to 2h, right? So you just plug in the values and find the probability. I will not do that, but you should do it as a homework exercise, right? So this is what the formula tells you. The formula is pretty complicated. It just, so the first term tells you the probability that it is actually fair given your hypothesis, and the second term is what is the probability that your hypothesis is true given the data, right? That's what we did. We just summed over all the hypotheses, right? Okay. So if you have seen the lectures, in the lecture, the professor has derived the value for, so if you remember when we were doing linear regression, we were calculating the cost function, right? So that actually comes from map hypothesis. In the lecture, the professor has talked about how the, gradient descent algorithm that you use on, or the least square error that you use for, minimizing your error, where does that come from? So the professor has explained in a lecture based on the map hypothesis for linear regression. Here I will do it for logistic regression. What is the map hypothesis for logistic regression, right? So for logistic regression, the error function is basically this log likelihood function, yi log yi plus 1 minus yi log 1 minus yi, and summation over that. So where does that come from, right? So here we will use the Bernoulli experiment that we are talking about earlier, right? So okay, log likelihood. So you see, so you take that x equals to some Bernoulli distribution. So what happens in logistic regression? You either get 1 or 0, right? Same as the Bernoulli distribution. Our outcome could be 1 or 0. And similar as Bernoulli distribution. That's why we take Bernoulli distribution. So which is basically P of xi, 1 minus P, 1 minus xi, right? And if you go for n Bernoulli trials, you will have x equals to xi, okay? And the product of P of xi times 1 minus P minus xi, right? So what do you have to do? You have to increase this probability, right? So this is a, uh, okay, you have to maximize this function to get the minimum error, right? So that, your probability is basically maximized, right? So what we'll do is just we'll take a log of this. So if you take log of this, what will happen is that the product will become summation, right? Because log of AB is log A plus log B. So this will become xi log P plus 1 minus xi log of 1 minus P, right? And then you take the uh, P value, which is basically making it maximum. So R max P, right? So this is where the log likelihood function comes from, right? I think the professor will explain more in the when she explains logistic regression in the next week, but I think this will give you a good idea about where it comes from, right? Yes. So you have to find so given xi, okay. So this is basically likelihood of P given xi, okay. So, given xi is basically your data, right? Your data points. So, given you are given some data, what is the value of p, which is best fitting your data, which is most likely fitting your data? That's what this likelihood function talks about. This is also called the likelihood function or the log likelihood function if you have taken a log of it. Right? So what is the value of p that maximizes your likelihood, which is best fitting your data? Given that you have some data xi, what is the value of p that is best fitting your data, which is maximizing your likelihood? So you have to maximize this thing, and that's what the log likelihood is, right? I think it's clear now, right? uh, Likelihood is the whole thing. So the whole thing I'm calling as likelihood, this thing, the summation. Okay. This whole thing is basically the log likelihood. Now you have to maximize this log likelihood. Sorry. Oh, sorry. Huh. I should, the summation is for the whole thing. Yeah. Right. And this is what is being written over here. Sorry. Come again. Where is theta? Okay. In the slide, you mean? Okay. Uh, okay. Base. You mean this theta? Okay, so I am using, you know, so what did I use? I think I used y for that term. So theta is basically the hypothesis. I used y variable, y equals to fair or y equals to unfair in the coin toss example, if you remember, right? So here they have called this as theta. So in my case, it was like y. Okay. 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 So, okay. Now, what is Bayes? Now we'll see Naive-Bayes theorem. So I think there was a lot of maths, but now I think it will be easier for us to, you know, understand this. Okay. So all those maths will come into play. So we'll go fast through this because we have done all the maths that is required. Okay. So, okay. So again, what is the probability that A1, A2, A3, and dot 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 till AN occurs? This is actually given by P of A1 given A2, A3, AN occurs times P of A2 given A3, dot 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 AN occurs, and so on, like, right? But if these events A1, A2, and AN are independent of each other, then this can be simply replaced by multiplication, right? As we said, uh, independence is basically multiplication, right? That we have established earlier. I mean, it's a naive way to think about it, but it works in this case. So P of A1 times AN is equals to P of A1 times P of A2 times P of A3 dot 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 till P of AN. And this is a diagrammatic representation of the thing that all the outcomes are independent of each other, but only depends on the cause. So this is something called a directed acyclic graph. So where you have a cause, and due to that cause, several outcomes can happen, right? So the cause could be you know a shift in tectonic movement, for example, that could cause an earthquake, that could cause a tsunami, that could cause, so many things. And all those outcomes are independent of each other. Let's say earthquake and tsunami are independent of the tectonic move. Earthquake and tsunami are independent of each other, but, you know, both are dependent on the cause, that is tectonic movement, right? So yeah, that could be used an example. So naive Bayes, what it does is basically it sees that okay, all my features are independent of each other, right? So I think it will be more clear if I go through this example. So let's say you have this example. These are the columns in your data. So first column is outlook. So you see whether the weather is rainy, overcast, sunny, and so on. What is the temperature, hot, mild, or cool? What is the humidity, high, normal? What is the windy? Is it like true or false? That means like whether it is windy or whether it is not, right? And so on, right? So this is how you look at the you know your data, and now this is your dependent variable. That is whether you are going out to play. Let's say you are playing cricket or anything. So if it's rainy, it's and hot and humidity is high and not windy, then you are not going out to play. And similarly, you have 13, like 14 observations, in which cases you are going out to play or not, depending on your weather, right? So here you see that outlook is independent of temperature, which is independent of humidity, which is independent of the windiness. So that is your naive assumption, right? So that is what this assumption that I was talking about earlier, right? So outlook doesn't depend on temperature, humidity, or windiness. But if you are going out to play or not, that depends on these things, right? So this is dependent on the independent variable, but the dependent variables are not, in between, has any dependence, right? Basically, the features do not have any dependence in between each other, right? So let me just solve one simple thing, and then so instead of solving the whole problem, let me just consider, I have one column and I'm just solving for that thing, so that you can get an idea about a whole data set together in using writing a code, right? So before I'll just explain the maths behind it, and after that we will solve the whole thing in code, how the namespace algorithm works. Okay. So this is my place. So I'm just picking out the first column, right? I'm not considering all the four columns, but instead I'm just considering the outlook column. And this is my target variable play. So I have like 14 observations. So if the outlook is rainy, let's say I'm going out to play. Outlook is sunny, going out to play. Overcast, play. Uh, and then again overcast, play, sunny, no, don't play, rainy, play, sunny, play, overcast, play, rainy, no, and sunny, then 0, 1, rainy, 0, overcast, 1, overcast, 1, right? So, yeah, so this is my data, right? So this means that, okay, the first day it is rainy and you're going out to play. Second day it is sunny, you're going out to play, and so on, right? One represents you're playing, zero represents you're not playing. Okay. Now, uh, you see, so now what you have to determine, so your what you are asked is whether you are going to play given that it is sunny. What is the probability that you are going out to play given that it is sunny? This is what you have to calculate. Okay. Now, how will you calculate this? We'll apply Bayes theorem. So this is equal to probability of sunny given that you are going out to play times probability that you are playing divided by probability that it is sunny, right? Okay. Now, okay. So how will you calculate the individual terms? Okay. So we'll see. So let's consider the first term first. Okay. The probability that it is sunny given that you are playing. This is the first term that you have to calculate. Sunny given yes. So now what we will do, we'll just, it has been given that you are playing, right? So this is the given. So we will select only those, uh, those rows where you are playing. So we'll select this row, this row, this row, this row. So wherever there is one, we are selecting them. And so how many are one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 times you are playing and 4 times you are not playing, right? So okay, before calculating this, let me just calculate what is the probability of yes. This will be actually easier to calculate because you see you're playing 10 times out of 14 times. So this is basically your probability of yes that you're playing. So that will be, I guess equal to 0.71. Okay. Yeah. So this will be close to 0.71. Okay. Now you have to calculate. Okay. Let's calculate the denominator first again. So probability that it is sunny. Okay. Okay. So how will you calculate whether the how many times it is sunny? So you see, like you take the total observations and you see how many times we have sunny. It is like 1, 2, 3, 4, 5. Like right, 5 times. Is it okay? Okay. No, out of the total. So right now we are not looking at the only yes terms. So out of the total, how many are sunny, right? So I am calculating the denominator first. So this term, the probability of sunny. We're not having any condition, right? So here it is out of the total, not condition. We'll see what will happen when we consider the condition. So probability of sunny is 5 out of 14. That will come out to be 0.35. And probability of sunny given yes. So now you consider only the yes terms and you see out of the yes terms how many are sunny. So this is sunny one. Okay, this we won't consider because this is a no term. This we'll consider. Again, this will not consider yes term. This will consider, right? So we will have three terms. Three times we have sunny out of how many yes are there? 10, right? So it is 0.3. Is that clear? How we are calculating these things? Okay, Kavita has raised a hand. Do you have any question? Is there a question? Kavita? Okay. So if not, yeah. So I guess it is clear, right? How we have calculated the probabilities. And now we'll just, plug in the values. Zero point 0.3 times 0.71 divided by 0.35. And whatever value you get, that is your probability. Zero point 0.3 times 0.71 times 35. That will come out to be zero point 0.6. Okay. So, so what is happening is that, so let's say you have been given these observations. This is your training data set. You train your model on this, and next time you get another observation which is saying that okay, outlook is sunny. Now you tell me whether I will go out to play or not. What is the probability that I will go out to play? So this is your probability. Your probability is zero point 0.6 that you will go out to play. So this is how the naive-Bayes algorithm works. And similarly, if you have multiple columns, you have to, condition on the multiple columns, right? So here you are considering only yes given sunny. So you will have to condition over other, like let's say the temperature is high or low and so on. And similarly, you have to see these probabilities again, right? This will be sunny high given yes. So if the, as I said, those two are independent, those features are independent. So you will just have to multiply them. Sunny given yes times temperature high given yes, and similarly so on, right? All if you have more columns, all those columns will just, all the probabilities will get multiplied for the consecutive columns. So that's it, right? So that's it to it. So now we will just quickly see see the whole column in example as an example, right? So if you can see my screen, so again here I am just loading my data set and printing my data set. So this is the data set that I have loaded, right? So if you see, these are the four columns and these are play yes or no. And so this in this step I'm just separating out my target variable. Yes. Okay, is it not visible? Is it visible now? Okay. So yeah, this is just, I'm looking at my target variable. This is where I am just, decoding my outlook and temperature. So these are string variables, right? So what I'm doing, I'm just assigning a value 1 to rainy, 2 to sunny, and so on, right? Sorry, I'm looking at the wrong column. Yeah, 1 to rainy, uh, 2 to sunny, and 0 to overcast, and so on. So these algorithms basically works with numerical values. So if you have any string values, you have to convert it to integers, right? So this is what is being done. Just simply convert. So this is basically the function what I'm using. So numerics dot fit transform. Earlier I have like defined numerics as label encoder. Okay, so this is what it is being done. Yeah, and then what I'm doing is that I'm just building for accuracy, which is 85% accurate. And then what I'm doing is that just inputting a value. So what I'm doing is that okay, I'm saying that whether my outlook is overcast, 0 for overcast, and the next column is temp 0. So I guess 0 represents cool, my temp, and my humidity is again 0, whatever that stands for. Wind is 1. So what will be my output, whether I will go out to play or not? So that is what my uh, algorithm is predicting. So it is saying, okay, yes, I will go out to play, and so on. You can like give anything, like you can give 2 instead of, okay, this is rainy or sunny or whatever, and then you will get okay. Now it is, you will not go out to play with this combination of weather. So this is giving out no, right? Is that clear? Okay. Okay, now we'll just move on to the last slide. Okay. Okay. So as we saw in naive-Bayes algorithm, is that all your features should be independent, right? But it might be the case that features might not be independent. It might depend on each other. For example, what you are trying to predict is whether you are going to office on time or not. It might depend on whether you have overslept or not, and overslept might depend on whether your alarm was on or not, right? So this is the dependence, right? So here you cannot apply naive Bayes because you have overslept or not depends on whether your alarm was on or not. So this is again what was saying earlier. This is a directed acyclic graph, and these are the conditional probability tables that uh, each node are associated with. I'll explain what this table means, but this graph basically represents that whether your bus was late or not. If your bus was late, in turn, if you have overslept or not, that will depend on whether your alarm was on or not. Where it comes in, where you cannot use Bayesian network. So I'll just explain uh, the conditional probability tables now, and then I will explain. We'll have an example of how to calculate this, whether you're on time or not, right? So okay, so basically this table is basically what is the probability your bus is late or not. So this is zero point 0.2. So there is 20% chance your bus is late, and there is 80% chance your bus is not late. Similarly, alarm on or not. And again, if you have overslept, so overslept, whether your alarm was on or not, it will have four values, right? So if you look at the table, so if your so what these values represent? So this represent that if your alarm is yes, alarm was on, and you have overslept, right? So that has probability 0.1. Similarly, this value talks about your alarm was on and you have not overslept. So that has probability 0.9. Not on, you have not overslept 0.1, right? So this is what the conditional probability tables talks about. Similarly, here it was bus late and overslept. So if bus late and overslept both are yes, then you're on time with probability 0.1, you're not on time with probability 0.9, and so on, right? So now we'll just look at an example, and we'll end up to calculate some uh, value. Let see. Okay. Okay. All right. Okay, we'll keep this on site. Uh, Let me do it into rating mode. Okay. And this is visible, right? I mean, the slide is not too small. I just have to take the values from there. So I'm just doing it side by side. Is there any questions in between? Okay. So let's say you have to calculate what is the probability that you are on time, given that you have, overslept. Overslept is yes, and your alarm was not on. So alarm on is no, it's not visible, right? Okay. Okay, okay, okay. Wait a minute. Okay, okay. Now it is. Okay, okay. Uh, so alarm on is no, and let's say your bus late is also no. So your bus is also not late. So you have to calculate what is the probability that you have you are on time, given that uh, you have overslept, your alarm was not on, your bus was not late, right? So how will you calculate this? So what you will do, you first start with, so okay, I'll just give you a technique how to do it. You start with the end node, okay? So end node is on time. So you do P of on time equals to yes. Now you see what does this node depend on? This node depends on bus late and overslept, these two nodes. Now you do that given that your what are the values of those parameters? Your bus late equals to no and your overslept equals to yes. Okay. So you just uh, put the two parameters which this node depends on, and you just put the values that were given in the question. Okay. So this is your first term times then what you do, then you go on to the nodes which are like above this, okay, or on the left of this node, right? So on time, and then the next set of nodes are burst late and overslept. So what you do is that you calculate P of burst late equals to no, right? What is the probability of burst late? No. Now you see that okay, burst late doesn't depend on any other nodes, so you just leave it. You don't have any condition on this node. Next, you move on to the other node, which is overslept. So what is the overslept value? Overslept is yes. Now overslept depends on alarm on. So you use condition on alarm on. So alarm on is no, right? Now these two nodes are over. Now you go on to the alarm on node, which is one node higher than this. So you give P of alarm on equals to no, right? Right. So this is it. Now you have gone to the end of all the nodes and you've covered all the nodes. So this is the formula that you will use, right? Okay. Now what are the values for each of the formulas? Okay. So I will say see from the table, the CPT probability that on time is yes, given bus late is no, overslept is yes. So bus late no and overslept yes corresponds to this row. This is the third row. And from the third row, you read the value. What is the probability that on time is yes? That is 0.3, right? So for the first one, the value is 0.3, right? Similarly, for probability that burst late is no is 0.8. From this table, you see 0.8 times what is the probability that overslept is yes, given alarm is no. So from this table, you see alarm is no, overslept yes, that is probability zero point 0.9, right? Zero point 0.9 times probability that alarm on is no. So alarm on no is zero point 0.1 probability, right? So this will give you whatever value this gives you. I think let me calculate 24946.0.0216. Okay. Okay. So this is how you read the table and calculate whatever has been given in the uh, question, right? So this will be the type of questions that you will get in exam. So you just have to read through a table. It is very mechanical. You just go first. Formulate this thing depending on the nodes, okay, and whatever the nodes they depend on. So you just write this out, and then you just see the values from the table. See each of the values from the table, right? And this just multiply it. Right? That's how you do it. Okay. Is that is that fine? Do you have any questions? Any questions, please? Really uh, tells you like how many person the probability of any two persons in the room having the same birthday is 50%, right? So if there are more than 365 people in a room, you would be sure that okay, two persons must have the same birthday, right? But you will be 100% sure then. But what is the how many persons need to be there in a room so that you are at least 50% sure that there are there are yeah, that two persons have same birthday. Okay, so think about it. This is a famous problem. You can like Google about it, and this just involves multiplication rule and the definition of probability. That's it, nothing else. So what is the map hypothesis for linear regression? As the professor has derived it, so you should look at it. In this lecture, we did it for logistic regression. You should know how to do it for linear regression as well. How do we get the least square function? And what are the assumptions? Yeah. So there are some of the assumptions that we took deriving the map hypothesis. So you should know what are the assumptions. And while performing a linear regression, you should be aware that whether your features, whether your data set obeys those assumptions or not, right? And we have seen an example of naive-Bayes algorithm and how it works. So you can we just saw it on a short data set. I think you should, like, the notebook will be available, the code will be available, so you can play with the code and get some data from the internet or Kaggle or whatever, and work it out yourself. Implement a naive algorithm, break it up into test and training set, train your data, and then uh, find the accuracy on the test set, do everything, and finally, yeah, you basically implement the naive-Bayes algorithm and check the performance. Maybe plot confusion matrix and uh, you know everything. Right? So that is it. If you have any questions for anything we covered today, please. Okay, so I think, uh, but I think the looking at the questions of the assignment, I think you will, some of the mathematics we have covered in this session. Uh, Based on those things, there are a lot of questions in the assignment based on basic probability theory and numericals. So this will help you in solving those questions.